Hello everyone, we are now on the last lecture of week 3. Week 3 is on digitization in communication systems. So, we have already discussed in week 1 that in many communication systems, even if the signal that you have to, a message that you want to communicate is analog, it is very often digitized, and digital equivalent of the analog signal is what is communicated to the receiver, where after due reception the digital signal is converted back to an equivalent analog form. Further, we also said that in all communication systems, whether the message is analog or digital, what's transmitted on the channel is very often analog, because channels, most channels are suitable only for analog signals. So, even if what you want to communicate is a digital signal, whether it originated from an analog signal or intrinsically discrete digital message, you have to convert it to an analog signal for transmission. So, there is a lot of analog to digital and digital to analog conversion going on, and this is what we refer to as digitization in communication systems. And we have talked about sampling, practical sampling, A to D conversion, D to A conversion, all of that we have considered now in the first 4 lectures. Now, we want to sort of spend a few minutes, this lecture is not going to be very long, taking those same ideas and looking at it particularly in the context of communication systems, transmitters and receivers. How do A to D converters and D to A converters get used in transmitters and receivers, right? So, we will talk about digital to analog conversion of the transmitter. Remember, what's transmitted on the channel is very often mostly an analog signal, and if what you have is a digital message to transmit, then you have to convert it to an analog signal, and that is done using very often nowadays for convenience, for effectiveness, for efficient implementations, all done using digital to analog converters. Similar, and then for this you have to use DACs, which to at the baseband signal level to get the analog baseband signals, and then you have to use quadrature modulation, which you may or may not have been taught this in week 2, but it's fairly straightforward. We'll look at what it is. The complement of this with the receiver is the received signal is analog, and if you want to do all your processing using DSP, again for effectiveness, for convenience, for flexibility and so on, then you have to do A to D conversion. And at the receiver, communication systems typically they employ bandpass signals. So, you will have to do what's called quadrature demodulation, and this may or may not have been covered in week 2, but it may come in week 4, but we don't need to know what actually happens inside a quadrature demodulator. We will just treat it as a black box. All we need to know is that it gives the complex baseband signal, real and imaginary parts of the complex baseband signal, its output, and then you have to use A to D converters to sample them. There is also a neat way by which you can, in certain cases, you can directly sample the bandpass signal, received bandpass signal, and directly, and in a very sort of a smart way, you can get the samples of the complex baseband, in-phase and quadrature components, and this is not used very often because the conditions under which this can be done, which we will mention, are not present in all receivers, but we should know that it's possible. I think the quadrature demodulation with baseband A to D converters is the most prevalent way in which analog to digital conversion happens in the receiver. So, let us dive into this a little bit. The transmitter of a digital communication system, as we said, maps message symbols to an analog signal for transmission on the channel, right. These message symbols I am assuming it's digital. They may come from digitization of an analog signal, and of course, if you're doing analog message communication over an analog signal, then this doesn't arise, right. We are talking about digital communication systems where you have to map messages to an analog signal, because the channel accepts only analog signals. As I already mentioned many times, this message symbol may come from an intrinsically digital message like a file or a text or ID of somebody, Or it could be actually digital messages, message symbols that come from digitization of an analog signal, a speech signal or a music wave signal or a video. We don't care. There are some digital message symbols that have to be transmitted and they have to be mapped to analog signals. And what is the best way, most efficient way in which this is done nowadays in transmitters? And the answer is the effective way of doing it is to compute the samples of the transmit signal, the analog signal, not the analog signal itself, the samples of the analog signal that you want to transmit, and feed them to a D2A converter, which will generate the analog signal so that it can be transmitted on the channel. Right? So this is a sort of a simple way to construct any sort of transmit waveform that you want to construct, however complex it may be. You don't have to worry about how to get circuits that will do that. Just compute the samples at the appropriate sampling rate, feed it to a DAC, low pass filter, and you have the signal ready for transmission. So what we are saying is you compute the complex baseband equivalent of the signal that you want to transmit. You want to transmit y of t. It has a certain y tilde of t, which is the complex baseband signal, y c of t plus j y s of t. We've studied this in week 2. We've also used it in understanding sampling and so on of complex signals earlier in this week. And the samples of this y tilde of t, which we call y tilde of n, they would be yc of n and ys of n, the real and imaginary part. These samples, using DSP, you compute them. You write programs, you write software, or you use digital logic circuits and compute them. And then you feed them to two DACs, one for yc of n, one for ys of n, and you convert them to yc of t and ys of t at the output of the low pass filter that follows the DAC. This is the smoothing interpolation filter. And then what you do, the equation at the bottom tells you what you have to do here, this equation, right? You have to take yc of t and you have to multiply cos 2 pi fct with it. You have to take ys of t and multiply sin 2 pi fct with it, and cos and sin of course have to be 90 degrees apart in phase, and then you have to add or subtract. It doesn't really matter if you subtract. This is the precise mathematical equation. If you put addition there, it just means you're transmitting minus ys of t instead of ys of t. It hardly matters too much. So you have to essentially create y of t, literally craft it in this fashion from samples of yc of n and yc of t and ys of t, that is yc of n and ys of n, which you compute, right, in programs and so on, right? So this is really the most effective and most flexible way you can change the program and change what you compute, what waveforms you generate, and so on. So you get receivers which have many modes of transmitters which have many modes of operation. Your cell phone transmits 2G signals, 3G signals, 4G signals, different bands, and so on. And all of this happens because it's highly programmable. This is how it's done, right? And so this is mostly how transmitters are implemented. There are two arms, each arm consisting of a DAC, a low pass filter, and then there is this the multipliers. Each arm has that, and you have to feed the two arms of the two multipliers, cos and sin. You have to have an analog circuit for that. You have to have the 90 degrees phase shifter, and you have to of course generate the cos 2 pi fct and sin 2 pi fct. I have shown an oscillator here. What is used in modern chips is a circuit called a synthesizer, which uses a PLL. In some other course you might have been taught PLLs, but we don't have time to get into that here. And you can literally, in a synthesizer, you can literally program the frequency that you want in a range, and it will generate that frequency, the cosine and sine at that frequency, right? And then you produce y of t, and y of t is a bandpass signal centered at fc with the particular spectrum and shape that you want, right? And so we use baseband D2A converters and quadrature modulation, right? And of course, like in any D2A conversion application, we can oversample the baseband signal, the yc of n and ys of n, so that the low pass filter that you use after the DAC is simple. So all of this we've talked about in an earlier lecture. And the oscillator, as I said, generates the carrier and its quadrature version, the sine 2 pi fct, right? And the two chains, the DAC, the LPF, and the multiplier, implicitly must have the same gain. Meaning, if you don't have the same gain, then what you are generating would be some alpha times yc of t cos 2 pi fct, and I don't know, and some beta times ys of t sine 2 pi fct, right? This is really what you end up generating if alpha and beta are not equal. And if alpha beta are not equal, of course, this is not what you want, right? So that is called balancing. So that these circuits, have to be balanced, and if you're making them with discrete components, this is a big headache. So all this the two DACs, the low pass filters, the quadrature modulator, all of these are usually built on one chip, and by design, the chip ensures the balance, right? And you could conceivably compute samples of y of t directly. It's a bandpass signal. You can compute the samples of y of t and feed it to a DAC. But of course, DACs sort of assume that the signal is low pass all the way from 0 to whatever frequency that half the sampling rate. And in this case, the actual signal is going up to the carrier frequency plus W. W is the baseband bandwidth. And so you will have to use a sampling rate which is greater than 2 times that. The fact that a lot of the spectrum from 0 to fc minus W is empty is not sort of something that the D2A converter is aware of. So it just treats it as a low pass signal all the way from 0 with the spectral content all the way from 0 to fc plus W. And Nyquist says you have to use a sampling rate greater than 2 times the maximum frequency in the signal, which is fc plus W. So you have to use sampling rate greater than 2fc plus 2W, which of course could be much higher than 2W, which is what you have to need, which is the sampling rate you need if you did the conversion, D2A conversion in the baseband. Because if you're taking yc of t and ys of t and yc of n and ys of n and converting them to yc of t and ys of t, they have bandwidth of only W, and you don't need such a high, you need a sampling rate greater than 2W. Now, if you try to feed samples of y of t to the D2A converter, your sampling rate has to be 2fc plus 2W at least, and fc can be large, so this can be not viable. If fc is small, in some applications it can be viable and you can do it. One example that comes to my mind is if you're generating the bandpass signal that is transmitted on a telephone line using modems. This was very popular in the 70s and 80s, 60s, 70s and 80s. So you have a modem and you transmit some low bit rate, a few tens of kilobits per second or even less on a telephone line. And the telephone line, the carrier frequency used was about 1,800 hertz, not very large. And the signal bandwidth was from about 300 to 3,300 hertz. So about 3 kilohertz bandwidth, centered at 1,800 hertz. Now, these are all small numbers, and you can easily sample it at 8 kilohertz, for example, which satisfies this 2fc plus 2W. And there's no problem, right? So there are some applications where you could generate samples of compute samples of y of t and generate y of t directly, but mostly we compute samples of yc of t and ys of t, that is yc of n and ys of n, generate yc of t and ys of t, then quadrature modulate them and get your y of t. This is usually the most common implementation at the transmitter. Now there's a dual problem at the receiver, right? At the receiver, you receive the same y of t, but of course now there's a noise added to it, which is also in the same band. Any noise that is not in the same band, you can put filter and remove it, so it really doesn't matter. But noise that is sitting spectrally on top of the spectrum of y of t, you can't remove it. And that is usually the model for the received signal r of t. And you can take the whole bandpass signal centered at fc and shift it to baseband, and that you would call r tilde of t. It will have an in phase and a quadrature component, rc of t and rs of t. This is exactly what you were taught in week 2. Now, how do you get rs of t and rc of t? There is a circuit or system that does that, and that's called the quadrature demodulator. This will be discussed in week 4 along with your discussion of AM, double sideband suppressed carrier and so on. So I will not get into the insides of what's in a quadrature demodulator. At the moment, we will just assume it's a black box. And what it does is you give it r of t or y of t, doesn't matter if you ignore the noise, it's y of t. It will give you rc of t and rs of t, or yc of t and ys of t, right? It will somehow take out whatever is modulating cos 2 pi of ct and whatever is modulating sin 2 pi of ct, separate them out and give it to you, right. That is what the quadrature demodulator does. And once you have these two signals, you want to sample them. They are all band limited signals. They are baseband signals, band limited to, let us say, W, and you want to sample them and get the samples of RC of t and RS of t, RC of n and RS of n at the same time instant, so that you can write a complex sample RC of n plus j RS of n, or if there is no noise, YC of n plus j YS of n, and they will be samples of y tilde of n or r tilde of t, y tilde of t or r tilde of t, right. That is what you want to do. So the clock that you feed to the two AD converters has to be the same clock, so that they are sampling at the same instant, and you get your samples, right. This is what you do in a receiver. So at the transmitter, you sort of do all the work that you want to do in digital domain, using either data computation or using digital logic circuits. Then finally, just before transmitting, you convert the samples of the in phase and quadrature signals to analog, quadrature modulate them, and you have your bandpass signal ready for transmission. At the receiver, you receive the bandpass signal as quickly as possible. First thing you do is you separate the baseband in phase and quadrature components using a quadrature demodulator. Then you use A to D converters. You don't need anti-aliasing filters, because the quadrature demodulator itself, you will see when you are taught that it has a low pass filter for extracting out RC of t and RS of t, and that essentially is also doubles as the anti-aliasing filter. And you just put A to D converters, two of them clocked with the same clock, and you get samples of the in phase and quadrature signals. And after that, whatever processing you want to do to ultimately extract the digital message, you do it all using DSP or using digital circuits, right. So anti-aliasing filtering before the ADC is usually a must, but here it's sort of inside the quadrature demodulator. That's why I didn't show it separately. And if the bandpass signal has a bandwidth of B hertz, when you shift it to baseband, it has a bandwidth of B by 2. So you have to, that's your W essentially, and you have to run the ADC at some speed greater than B, the usual Nyquist 2 times the bandwidth or more. And if the low pass filter or the anti-aliasing filter, it's the same thing, the same filter. If it has a gentle transition band, then we've already discussed this, you sample it at a rate much greater than B, and then in the digital domain you filter it back tightly to B hertz, and then you to B by 2 hertz, and you downsample it, decimate the sampling rate down to something close to B, right. Just as in the quadrature modulator, the quadrature demodulator also, the two arms, there are two arms, right. There is something in the quadrature demodulator that separates out the signal into the RC of t and RS of t, and then there is the A to D converters. Those two arms again have to have the same gain, they have to be balanced, and again therefore they are all built in one chip, and you just procure the chip, feed the two signals, and balancing is ensured, right. Otherwise you have the same problem as we discussed with the alpha and the beta, and what you have as the complex baseband signal is not the complex baseband equivalent of the bandpass signal, it is something else because of the alpha and the beta. Finally, I want to point out to you that it's quadrature demodulation followed by twin A to D sampling is not the only way to get samples of YC of t and RC of t and RS of t, or YC of t and YS of t if you ignore the noise. There is a way that you can do it directly from the bandpass signal in some situations. So in some radio receivers, and this used to be true in fact of all radio receivers till maybe 10-15 years ago, because you will I don't know whether we will have the occasion to tell you about different types of radio receivers in this course. Maybe there will be, I don't know, but there is a very well-known architecture for the radio receiver. The radio receiver means the receiver starting from the antenna down to the, before you get to the baseband signal. There is a very famous architecture that sort of works for all carrier frequencies, all channel bandwidths, and so on. It sort of makes the filtering problem. You have to, because in a radio receiver you have to pick out the channel that you want, and how you do that is a challenge, because if the filter bandwidth is fixed but the center frequency keeps going up, then you might be knowing from your basic course on circuits that the Q factor of the filter goes on increasing and becomes harder to build. So to avoid this problem, a radio receiver architecture that's called a super heterodyne receiver, where the channel that you wish to select is brought to a particular frequency called the intermediate frequency by shifting the spectrum. Shifting spectrum is quite easy. You just multiply it with an appropriate sinusoid and you can do that. And once the desired channel comes into at the intermediate frequency, then you sort of put a fixed filter of a fixed Q and select it out. This is a very interesting idea that was developed nearly 100 years ago, and it has stayed. It has, there are some implementation efficiencies that you get if you can avoid this and bring the signal directly to baseband, channel that you want directly to baseband. And today many chips like the ones in your phone do that, particularly for highly integrated solutions. That's quite good. But there are receivers that use this super heterodyne architecture, and the desired channel, whatever it is brought to a fixed intermediate frequency, and all other channels are removed. So what you have at the output of that, at the radio receiver at that point, is just the desired channel at a particular frequency which is fixed, even though it might have been received at some other frequency, right? And the channel bandwidth is some B hertz. In such cases, where there's no other signal in the receiver except noise, of course, and the desired signal, R of t is the signal that you want, Y of t centered at this IF, and there is noise, of course, that I've shown in this picture, but there's nothing else. Everything else in the spectrum is clean. There are no other channels next to the desired channel and so on. In such cases, if you ignore the noise, then what you receive is a desired signal at IF, right? Not at the carrier frequency FC, but at the intermediate frequency IF. And both the in-phase and quadrature components, YC and YS of t, are band limited to B by 2, as usual, right? Now let us sample R of t at some rate greater than B, right? Where B is the bandwidth of the bandpass signal. But let's make sure that the IF frequency is not anything, but it has a particular relationship to your sampling frequency. It is some multiple of the sampling rate. So let's say you have satisfied this constraint that the IF frequency is a multiple of the sampling rate and your sampling rate is greater than B. If you calculate cos 2 pi FIF of t, 2 pi FIF is m by t, and you sample at t equal to nt, right? So if you sample it at t equal to nt and you substitute if you substitute for FIF, then what you find is that at all the sampling instance, it is cos 2 pi mn is always 1, irrespective of m and n. Any sampling instant, any value of m, this is always 1, right? And sin 2 pi FIF t, which is sin 2 pi mn, is always 0. So what happens is the samples of R of t taken at nt, right, will just be the samples of YC of t taken at nt. YS of t just disappears, right? And that's YC of n. That's what you want, and the sampling rate is also suitable for the bandwidth of YC of t, which is B by 2. So any sampling rate greater than B is fine. So you see, I've got the samples at the sampling rate that I want of the in-phase component YC of t by just sampling the bandpass signal. I didn't need a demodulator and so on, right? What do I do to get YS of t? Well, there's a similar trick. You do the sampling at the same rate, 1 by t, but you have a clock phase which is offset by t by 4, 1/4 of a sampling interval. You can substitute now and verify that the cos will now always be 0 and the sine will always be 1 or minus 1. It doesn't matter, but it will always be 1 or minus 1, right? 1 or minus 1, not alternate or anything, just 1 or minus 1. And therefore, the samples of R of t obtained at the same sampling rate but at an offset clock will be samples of either plus YS of t or minus YS of t at the same sampling rate, which is sufficient for that bandwidth, but at an offset clock phase. So you see here, I've got samples of the in-phase and quadrature components yc and ys of t at the desired sampling rate without any demodulation. And the reason I was able to do that is because sampling is a multiplication process with an impulse train, and multiplication with an impulse train is also demodulation. So actually there's demodulation going on when you sample. I don't do any separate demodulation, and I actually can get these samples, but they are not at this, the sampling is not happening in the two signals yc of t and ys of t. It's not happening at the same time instant. It's happening with an offset clock phase. And therefore what you have to do is, in the digital domain, you have to take the samples of ys of t which you have at certain time instance, and you have to interpolate samples t by 4 away, right? And that you can do. We all know how to build digital interpolators. You can use software to design the interpolator, because Nyquist tells you that you can interpolate any sample in ys of t, right? Your sampling rate is sufficient. So you interpolate these samples. For every input sample, you interpolate one sample, which is t by 4 away. And now you have samples of ys of t which are at the same time instant as those of yc of t. And you can combine the two to get samples of y tilde of t. So there is a way to directly sample the bandpass signal. You don't need a quadrature demodulator, but only if the receiver gives you the bandpass signal with nothing else, no other bandpass signals, other channels sitting there, because then there'll be a problem if you sample it, right? You have to remove everything else. Noise, of course, sitting on top of the desired signal is acceptable, is unavoidable, but everything else, the spectrum should be clean otherwise. And the IF frequency selected should be having this relationship that it should be a multiple of the sampling rate that you want to use, or the sampling rate that you use must be a sub-multiple of the IF. So this is, I'm not going to belabor this too much because this is not used much in practice. These conditions are difficult to meet, and as I told you, many receivers today don't use this, this super heterodyne structure with IF frequencies, but you should know that it's possible, right? So what are the key takeaways? A DAC is frequently, DACs, actually two of them, are frequently employed at the transmitter to construct the analog transmit waveform from samples that are computed using DSP, the samples of the in-phase and quadrature components. They are computed and they are fed to twin DACs followed by a quadrature modulator to generate the transmit signal. And these two arms that process the in-phase and quadrature signals have to have the same gain, and that's, in other words, they should be balanced, and this is very important. Similarly, the receiver usually has a quadrature demodulator followed by twin ADCs that are clocked together, and again these two arms have to be balanced. And it's useful to know that there is a way to avoid the quadrature demodulator if some other conditions are satisfied. Conditions being that you have only the desired bandpass signal with noise, no other spectrum, no other signal is there in this input signal that is being sampled, and you choose a sampling rate which is a sub-multiple of the IF frequency. And then you can sample the bandpass signal itself and get samples of the in-phase and quadrature components ys of t and in-phase should be yc of t, I'm sorry, this is a mistake. This should be yc of t, and quadrature signal ys of t, and you can actually, they will not be at the same time, same sampling clock phases. Ys of t will be sampled at a different clock phase, and you have to interpolate the samples back to the same clock phase as that of yc of t, and then you can combine them to get a complex signal y tilde of t, or samples of y tilde of t, y tilde of n. So otherwise you can't just take the real part from yc of n and imaginary part from ys of n. There are different sampling instances and write them together. You can't do that. You have to interpolate the samples of ys of n to the same sampling instance as those of yc of n, and then you can combine one sample of yc of n and one sample of ys of n together as a complex sample to represent the sample of y tilde of n. This is not used very often, as I already mentioned to you. It's not as common as quadrature demodulation with twin ADCs, but keep in mind somewhere that it is possible to do this. You may find it happening in some implementations. You should not be surprised. So with that, we come to the end of week 3. I think we have sort of taken a good view of all the important things regarding digitization in communication systems, regarding sampling, regarding A to D conversion, regarding the use of sampling, A to D conversion and D to A conversion in communication systems. Course questions, as always, are welcome on Discourse, and hope to see you next when I come back to you in week 5. Thank you.